Uh, I'll talk about the gap statistics and correlations in random average process on a ring with a tracer particle. In fact, I'll talk about some exact results about the gap statistics and also about 2-point correlations. So this work is done in collaboration with Julia Sividini, David Mukamel, and Sottu Mujumdar, who is here. So what is random average process? It's a process defined on a continuous line while particles are moving, and the particles are moving as follows. So a particle in some small time interval dt tries to jump to the right or to the left with some rate, and whenever it jumps in one direction, it jumps by a random fraction of the space available till the next particle in that direction. And the random fraction, the eta, is chosen from some distribution R eta. For example, in this picture, the ith particle in some small time interval dt starting from position xi, if it moves to the right direction, it jumps by a random fraction of the space till the I plus 1th particle with this probability. And if it moves to the left direction, then also it moves by a random fraction of this space with a probability this, and it doesn't move with 1 minus dt probability. And that describes the dynamics of the particles in this process. This process was first introduced by Ferrari and Fontes in 1998, and this process appears in various physical situations like in random average, in traffic model, in wealth distribution models, in the interface height models, also in force fluctuation, granular media, etc. So in this talk, I'll consider random average process on a ring. So I consider a ring of size L where n particles are moving, among which one particle is special in the sense that it moves to the right with rate p and to the left with rate q, whereas all other particles, which are rate particles, they move to the right or to the left with equal rate half. And for this setup, the quantities we are interested in are the gaps between successive particles, which is this gi, which is the position of the I plus 1th particle minus the position of the ith particle. In particular, we are interested in the joint distribution of the gaps in the steady state for these two cases, p equal to q case when all the particles are moving symmetrically, and the second case is p not equal to q, this special particle, which is the tracer particle, which moves asymmetrically, that is, it is driven. For these two cases, I would like to study this quantity. So let us start with this p equal to q case. So in this case, all the particles are moving symmetrically. So obviously, for different choices of the jump distribution, this joint distribution will be different. And for arbitrary jump distribution, finding this joint distribution is relatively harder. So let's consider a relatively simpler question. Is it possible to have the joint distribution in the following product form, factorized form, where this delta function represents the global mass conservation, which is basically because of the fact that the length of the ring is fixed. So is it possible to find out the joint distribution in this product form? And if so, then the next question is for what choices of our jump distributions? So the answer to this question is that if the jump distribution satisfy this integral relation for all positive u, where beta is some parameter related to the first moment and the second moment of the jump distribution, explicitly given by this. If the jump distribution satisfies this relation, then one can show that the joint distribution of the gaps is factorized, and it's given by this explicit expression where the weight functions are same for all I, and they're given by this kind of power laws, where ZNL is the normalization constant. And this distribution has some universal features, which are as follows, that this distribution does not depend on the explicit forms of the jump distribution R eta, which have same beta and also satisfy this relation. And it also does not depend on the jumping rate of the tracer particle. And even when the individual particles have their own rates in this following form, that the rate to the right is Zi plus R and rate to the left is Zi minus R, in such a way that the rate to the right minus Z to the left is some constant, then also one can show that the joint distribution is given by this product form. So you see that whenever jump distribution satisfies this relation, the joint distribution is given by this factorized form. Now the question is, what are the solutions of this equation? Can we find out some solutions of these equations? So in fact, there are many solutions, infinite number of solutions of these equations. We could not find all the possible solutions, but we found many solutions. And we tried to categorize them according to the values of beta. So for beta is this parameter. So for beta equal to 0, one solution is this delta function. Beta equal to 1 is a very interesting case, because for this case all the possible solution can be expressed in terms of this in this expression in terms of this function, which is a symmetric function, symmetric about half and also normalized. And one can find many solutions. One such example is this beta distribution. There are many other examples also. General beta, for general beta we can find one solution which covers the whole span of beta, which is 2 beta times 1 minus eta power 2 beta minus 1, and this covers the full range of beta. And note that for beta equal to half, this gives you the uniform distribution. Large beta case is also interesting, because in this case the solution of this equation can be expressed in terms of this kind of scaling function, where the Laplace transform of this scaling function satisfies this relation for all positive u. And there are also many solutions for this equation. One class of solutions can be obtained by the ratios of polynomials, which I am not discussing here. So one example of this kind of solution is this exponential distribution. So we see that for R eta, this equation has many solutions, and for those R etas, the joint distribution is in this factorized form. So what about other joint jump distribution which does not satisfy this relation? So obviously for those jump distribution, the joint distribution is not factorized, but in the thermodynamic limit, this distribution in the leading order is factorized, and the local distribution functions are given by these gamma distributions. However, these in the next order, at order 1 over n, this there are deviations from this factorization property, and those deviations are quantified by the correlations. So we looked at the correlations also. So for any arbitrary jump distribution, this correlation can be computed for any I and j, and here this is the exact expression of this. Or you see that there is this Kronecker delta, which because of that you see that for large n, the diagonal correlation, that is for I equal to j, these are of order 1, whereas the non-diagonal off-diagonal correlations are of order 1 over n. So all these things are for p equal to p case, when particles are moving symmetrically, all the particles are moving symmetrically. So let us now consider the case when the special particle is driven, that is p not equal to q. In this case also the joint distribution of the gaps is not factorized, and again in the thermodynamic limit, this joint distribution will have a factorized form in the leading order. But now the local distribution functions are dependent on I. For which gap you are writing this distribution depends. Although this distribution are expressed again in terms of the gamma distribution, but this gamma distribution depends on some parameter which is the ith average gap, which changes with I. And this is because of the driven motion of the tracer particle. And once again, at order 1 over n, there is the deviation from this factorization property, and this deviation again can be quantified by the correlation. So we are interested next to find out the correlation, what kind of correlations are there when the tracer particle is driven. So we find, so starting from the master equation, you can write down the equations for these correlations, which are defined by this. Mi is the average gap, and you can write down discrete equations from this, and you can try to solve this. We find that these correlations, the off-diagonal correlations are of order 1 over n, whereas the diagonal correlations in the leading order is of order 1, and they have this kind of scaling behavior. They satisfy this kind of scaling behavior in the large n limit. So we find out these scaling functions explicitly, the large n limits, in the continuum limit. And these scaling functions, they satisfy these following continuous relations. So the C0x, which is the scaling function associated to the diagonal correlation at order 1, this is given by this explicit expression, where P and Q are the rates of the special particle, tracer particle, mu2 is the second moment of the jump distribution, and mu1 is the first moment of the jump distribution. And we see the C0 x is a quadratic in x. The scaling function associated to the off-diagonal correlation, this function, satisfies this differential equation. This is the Laplacian, and this differential equation has to be solved in this unit square, where this inhomogeneities comes from the usual the diagonal fluctuations, and they appear on the diagonal. And this equation has to be solved with these discontinuous boundary conditions, because this boundary conditions comes from the fact that the pressure particle is driven, and that introduces the discontinuity in the this function, and also introduces inhomogeneities in the problem. Moreover, this equation has to be supplemented by this relation, which comes from the fact that the total mass is conserved, which is the length of the ring is fixed, L. So one has to solve this equation, and one can solve this equation, and the solution is given by this, where this is the homogeneous part, and this is the particular integral part, and which is written in terms of this Green's function, which is defined by this. Here you note that the Green's function is not defined in the usual way, because this charge distribution actually does have total charge is 0. So you have to add some extra charge here, so that total charge becomes 0 here. And one has to solve this Green's function using, again, satisfying these boundary conditions. And one can find out the solutions for any Q and P. Here I am writing the solution only for Q equal to 0, which looks kind of big and complicated, but it's not so complicated. And one can find the solutions for any P and Q following the similar procedure. And once we have the Green's function, you can write down the explicit expression of this the scaling function, and you find out this constant, which I wrote, A, using this relation. And you have this explicit expression of this scaling function. And we try to verify this scaling function from the numerical studies. So what do? We compute Dij for different number of particles, different n, and plot n times Dij as a function of the scaling variable x equal to I over n plus 1. And we see that for fixed j, these functions for different, these values for different n, they collapse on top of each other. And this collapse function match very well with the theoretical curve, which is the solid black line. And the three different plots are associated to three different fixed values of j. This is for n by 4, n by 2, and 3n by 4. A similar verification we have done for the diagonal correlation also. And in the diagonal correlation, you see that in the leading order there is this scaling function. Then also in the next order there are different scaling functions. So this verifies this order, where we see again that the different values, data for different values of n also collapse on top of each other as you increase n. And here you note that we are not plotting n times this. This is just Dii versus the scaling function I over n plus 1. And this solid line is basically this expression which matches with this. And the inset verifies the information of the scaling function in the next order, which I'm not going into the details. So we studied the random average process on a ring with this driven pressure. When the pressure particle is not driven, then there are some choices of jump distribution for which this distribution is product. But when it is driven, then it is factorized in the leading order, and there are order n corrections which reflects the deviation from this factorized property, and those are quantified by the correlation which satisfy these scaling relations, and we find out these scaling functions explicitly. Thank you.
Questions?
So where you say that for P equal to Q case,
Yes.
Yes. The distribution is factorized in 1 by n, in the order of 1 by n. Yes. It is factorized.
Yes.
But in general, it is not true, because the model studied by Satya and Rajesh, so that model is related to this model, no?
Yes, yes.
But there are non-trivial correlations, I mean, for certain cases.
Yeah, here are also there are correlations. Like
no, but 1 by n, that vanishes.
At order 1 by n, there are...
no, but there are finite correlations.
No, for this model, there is no correlation.
So it's a special case, I mean...
No.
But this is symmetric, no?
Yeah, I mean...
Equal to Q.
There is no correlation.
Okay, probably we'll talk later. I'm a bit surprised.
Sorry? Yeah, that also we have done, but yeah, it also has very non-trivial structure. But it has some scaling behavior, and that scaling is C I J T is some. It has this kind of scaling behavior in T going to infinity, and you can find out this function also. No, this I am talking about on the infinite line. If you start from ring, then we see a crossover only for the mean position of the tracer particle, not for the fluctuation. And this is a very recent result.
Question here for now. Thank you very much.